In this video, we're going to look at the unit tangent and the unit normal vectors. And so we're going to calculate unit tangent vectors. Now, we've already looked at tangent vectors, and we're going to see how unit tangent vectors can help us find these things called unit normal vectors, or any normal vectors for that matter. So let's let r of t be a smooth function on an open interval. So I can take the derivative. Now, we've seen that the tangent line moves in the direction of r prime of t. If we make that directional vector a unit vector by multiplying 1 over the length of r prime, then we've created the vector capital T, which is the unit tangent vector. So we take the derivative and we essentially make that derivative vector length 1. That becomes the unit tangent vector. And as we've seen, that is moving in the direction of the tangent line. So let's go ahead and compute the unit tangent vector for this example. We have our function, our vector valued function r of t as 4 cosine t, comma 4 sine t, comma 1/2 t. We'll compute the unit tangent vector, and then we'll compute what happens when you plug in 0 and what happens when you plug in pi over 3. In order to calculate the unit tangent vector, I first need to find the derivative of r. So we're going to find the derivative of r. Obviously, that is with respect to the variable t. Derivative of 4 cosine is going to be -4 times sine of t. Derivative of 4 sine of t becomes 4 times cosine of t. And derivative of 1/2 t becomes 1/2. So that is my derivative. Now, in order to create a unit tangent vector, I'm just going to take that derivative and I'm going to multiply by 1 over the magnitude of that derivative vector. Now, in this case, some nice things happen when I find the magnitude. So magnitude is going to be square root of -4 sine of t squared plus 4 cosine of t squared plus 1/2 squared. So that's my magnitude. And then I'm going to multiply by the actual derivative vector itself. And there we go. Now this looks messy right now, but in this case, it actually cleans up pretty well because that magnitude there can be simplified. -4 sine of t quantity squared becomes 16 sine squared of t. 4 cosine of t squared becomes 16 cosine squared of t. And hopefully you know by now that sine squared plus cosine squared gives you 1. So if you factor out a 16, we get 16 times sine squared plus cosine squared, which just gives me 16 times 1. This is a trig identity. Sine squared plus cosine squared is equal to 1. Hopefully you've seen that before. So we get 16 times 1 plus a half squared. A half squared is a quarter, which I'm going to write as 0.25 just for the sake of ease. So I get 16 times 1 plus 0.25. That is just 16.25 when I simplify it. So my unit tangent vector is going to be this constant multiplied times the derivative. This is a really nice feature because our derivative had constant length. We got some really nice unit tangent vectors. Okay. And if I want to find a unit tangent vector at a certain value for our variable t, all I have to do is plug in those values. So in this case, when you plug in 0, you're going to get 1 over square root of 16.25. When you plug in 0 into sine, you get 0. So 4 times 0 gives you 0. When you plug in 0 into cosine, you get a 1. Therefore, the y component is a 4. And when you plug in 0 into a constant, you just get the constant. So you get 1/2. So that is my unit tangent vector when I plug in 0. You can check that that's going to be a unit vector if you want. I'm not going to right now, but if you'd like to, you can. Let's do the same thing when we plug in pi over 3. When I plug in pi over 3, first off, I have this coefficient out front. I like keeping it out front. Some people may like distributing it into each component. Either way, it's fine. I like keeping it out front because of some things we'll do later. And then when you plug in pi over 3 into sine, you get root 3 over 2. So what you're getting for your x component is -4 times square root of 3 divided by 2, which is just going to be -2 root 3. That's what I get for my x component. For my y component, when I plug in pi over 3 into cosine, I get 1/2. 1/2 times 4 becomes 2. And then obviously my z component, nothing to plug in there. I just get 1/2. So that's the unit tangent vector when I plug in pi over 3. If we want to see a visual of this, I graph this. Again, don't worry about how to graph this right now. That's not the important part. I just want you to see what's going on. And what I've done is I've created a point which can be slid along this curve. Right now, this is the point when the t value is 0. And you see that the unit tangent vector is going in this direction. So it's going traveling in the same direction that the curve is traveling in all dimensions, all 3 dimensions. And if we move that point along, the unit tangent vector is going to be moving along the curve, but it's going to be pointing in the direction of the travel of the curve. Now notice that in my case, this unit tangent vector is pointing kind of up and to the right. That's because as t is increasing, my point along the curve is moving up and to the right. So it is pointing in that way, direction of the curve as t is increasing. So that's the unit tangent vector. Now we've made the unit tangent vector always have length 1. We're forcing it to be a unit vector for a couple of reasons that we'll see later. Obviously, there's tangent vectors of any length other than 0. So we forced the tangent vector to be length 1. So that's what's going on. Let's do another example. Let's compute the unit tangent vector, capital T, and then compute what happens when we plug in 1 and what happens when we plug in 3 for this vector valued function. R of our variable t is equal to 5t squared plus t, comma, 2t minus 1, comma, t. So we have this vector valued function, and we want to find the unit tangent vector. Just like in our previous problem, we're going to start out by taking the derivative. So derivative of r is going to be r prime, which is 10t plus 1, comma, 2, comma, 1. So that's my derivative. Now notice that the derivative, unlike our last example, has varying lengths based on different values of t. In our previous example, my derivative had constant length of square root of 16.25. Here, if you look at the magnitude is going to vary depending on what value of t we plug in. And that's fine. That just means that when I take my unit tangent and I create the vector, that constant out front is not going to be super constant. It's going to be square root of 10t plus 1 quantity squared plus 2 squared plus 1 squared. I'll simplify that in a moment, but before I do that, let's make sure that we're all on the same page. We're multiplying that by our 10t plus 1, comma 2, comma 1. I'm going to expand this out. If you take 10t t plus 1 and square it. That, well, let me do it on another line. That is going to be 100t squared plus 10t plus 10t, which gives you plus 20t, plus 1 plus 1 times 1, that's plus 1. Notice that 1 plus 2 squared plus 1 squared combine to give you a plus 6. So that is the unit tangent vector we're looking for. Or at least that's a simplified version of it. Again, different values of t are going to give you different directions. The derivative is a different length, but the unit tangent vector is always going to be length 1. So while the derivative is going to have different lengths, the unit tangent vector is always going to have length 1. Now we're going to visualize this one as well. This one, when I created the tangent vector, I didn't make it length 1, just so that it sort of sticks out more and it's easier to see. If you make it length 1, it's pretty short. So I didn't want to make it length 1. So this is the tangent vector, but it's going to be a longer length there. But you can see kind of what's going on. As we move along this path, the tangent vector at whatever point we are at is traveling in the direction of the path of our curve. You can see that the vector valued function gives you this curve that looks similar to a parabola. And as the t increases, as the point gets higher and higher and higher, we're traveling around, but the tangent vector is always pointing in the direction of how the point is moving along this curve. So tangent vector, again, I didn't make this one a unit tangent because it's hard to see if it's a unit tangent, but I think you get the idea. Now, lastly, just to calculate it, when we plug in a couple of values, let's plug in 1. If I plug in 1, 100 times 1 squared plus 20 plus 6 becomes 126. That's going to be my underneath the square root. When I plug in 1, I get 10 times 1 plus 1. That's 11. And so I get the derivative would have been 11 to 1. The derivative vector would have been 11 to 1. If I multiply that by 1 over square root of 126, that will be of unit length. If I plug in a 3, what happens is I get 100 times 3 squared plus 20 times 3 plus 6. I get 966 underneath this square root. And then when you plug in a 3 here, 10 times 3 plus 1 is 31. And you can double check and make sure that 31 to 1 has magnitude of square root of 966. Therefore, if we multiply by 1 over square root of 966, then we have a unit vector. So again, I'm not going to check that by hand, but if you want to, you can check that, that these are unit vectors, these two here. And in every case, we get a unit vector. So that is the unit tangent vector. It's basically my derivative made into unit length. Now let's look at another concept called the unit normal vector. So we're going to start out with some vector valued function r of t, and we're going to make it a smooth function so that we can take derivatives and that we can have a unit tangent vector for every value of t. The unit normal vector is the derivative of the unit tangent vector made into length 1. Now, be careful. This is not the second derivative of r. Because of that, forcing my unit tangent vector to be length 1, we don't get the exact same thing. So this is the unit tangent vector. Take that derivative and make it length 1. Now there's a lot of tricks to this, but a lot of algebraic tricks to how to take a derivative. Sometimes it's pretty easy, sometimes it's harder. We'll see in the two examples that we did how to take a unit normal vector. Before we do that, I want to say something about the unit normal vector. The unit normal vector comes from taking the derivative of a vector of constant length. Remember, our unit tangent vector always has to have length 1. Since we forced our unit tangent vector to have length 1, the unit normal vector comes from the derivative of constant length. And that means if you take the unit tangent and dot product it with the unit normal vector, you get 0. In other words, what's happening is that the unit normal vector is pointing in a direction that's orthogonal to the direction of the curve. So unit tangent vector is pointing in the direction of the curve. The unit normal vector is pointing orthogonal to the direction of the curve. And again, that is coming from this trait about derivatives. If I have a vector valued function, dot product with its derivative, it becomes 0 as long as the vector value function has constant length. If the vector value function does not have constant length, then this is not a true statement. But since my unit tangent has constant length of 1, then its derivative dot producted with itself is going to be 0. And if I take the scalar or any scalar times that, it's still going to be 0. So unit normal vector is pointing in a directional that is orthogonal to the curve. By the way, it's always pointing in the concave direction as well. I will go over that when we do an example. So let's take a look at this example that we had earlier. Earlier, we calculated the unit tangent vector. Now let's calculate the unit normal vector. And then we'll plug in 0, plug in pi over 3, and see how that works. This is the vector valued function given by 4 cosine t, 4 sine t, and then 1/2 t. Now, when I do this, I want to be a little bit clever about how I go ahead and do this. So obviously you can do it long way, but I do want to show you this. Because of the following fact, if you multiply by a real number, if I multiply my tangent vector by a real number and then take the derivative, we're going to get the same unit normal vector. So I'm perfectly okay. Since this is a scalar out front, I can simply multiply this unit tangent vector by a scalar. Again, it has to be a real number scalar. It cannot have any t's in it, any variables in it. But I can multiply times a real number and then take the derivative and then do the same calculation with just the scalar times unit tangent. So in other words, I can use any tangent vector. It doesn't have to be a unit tangent as long as I'm not getting rid of variables here. So I say all that to say, instead of using the actual tangent vector, let's go ahead that. I'm going to multiply that tangent vector by square root of 16.25 for the obvious reason that I want to get rid of this coefficient out front and make my life a little bit easier. So then I'm going to take the derivative of that thing. I'll call this just c, some constant. I'll take the derivative of that thing. Now the derivative of that is going to be -4 times cosine of t. Derivative of cosine is negative sine, so I get -4 times sine of t. Derivative of 1/2 is 0. So if I'm finding the unit normal vector, I'll do that down here. All I have to do is take this vector, that's my constant, times derivative of unit tangent. And then make it unit length. If I make it unit length, I go 1 over square root of -4 cosine of t quantity squared plus -4 sine of t quantity squared plus 0. And similar to what we had before, we're going to have 16 cosine squared plus 16 sine squared plus 0. When I do that calculation, I get 16 plus 0 under the square root. Square root of 16 is 4. So I'm going to be multiplying everything by a 1/4. In this case, it makes sense to multiply in because 1/4 times -4 is -1. 1/4 times -4 is -1. 1/4 times 0 is 0. So my unit normal vector turns out to be really nice. Negative cosine t, negative sine t, comma, 0. Now you could have done that whole thing with this coefficient attached. Again, this is a real number coefficient. So the derivative property works fine because I'm multiplying by a real number. But I could have done that whole thing with this attached. If you'd have worked through it, you would have gotten the exact same unit normal vector. It would have just been a little bit messier, and you'd have had square root of 16.25 canceling out at some point in time. So that's the unit normal vector in this case. Let's go ahead and graph that. Oh, I'm sorry. Before I do graph that, let's say we want to take this unit normal vector and plug in a value like 0. What would we get? Well, plugging in 0 would give me negative cosine of 0. That gives me a -1. Plugging in 0 gives me negative sine of 0. That gives me 0. And I get another 0. So I get -1, 0, 0 as my unit normal vector when I plug in 0. Obviously, that's just the vector -I, where I is the standard unit vector. So that's what we get. Let's plug in pi over 3. Well, if I plug in pi over 3 into cosine, I get 1/2. So if I plug in negative cosine of pi over 3, I get negative 1/2. Negative sine of pi over 3, that gives me a negative √3 over 2. And then obviously there's nothing to plug in for 0, so you get 0 as your z component. So plugging in 0, plugging in pi over 3 gives you those two vectors. Now let's go ahead and see what this normal vector looks like if we draw it on the graph. So here we have our unit tangent vector. That's the one in red. Our unit normal vector is the one in green. So notice that our tangent is moving in the direction of the graph. Our green is perpendicular or orthogonal to that unit tangent vector, and it's pointing in the concave side. It's pointing inward towards the graph, bending in the concave direction. They are orthogonal. If you look straight down, you can see that they're hitting at 90-degree angles. excuse me. And that works for every vector or every point. So if we start really low on our graph, we get a point down here, and tangent is always pointing in the direction of the travel. And the unit normal vector is always pointing in a direction orthogonal to the travel. By the way, this is the one we found. We found the unit tangent when t was 0 and the unit normal when t was 0. That's why we're getting -1, 0, 0. It's pointing straight, in this case, towards the z-axis. But we can move up and along, and that's what's happening. So unit tangent, once again, is in red. Unit normal is in green. So the normal vector is really nice to have because we have now a tangent which tells us the direction of travel. And now we have a normal vector which is orthogonal to the direction of travel. Let's do the other example that we dealt with. Let's take this vector valued function, which has its components determined by polynomials. And let's compute the unit normal vector for it when, in general, first off, and then also we'll plug in 1 and plug in 3 into our variable. Now, this one's going to be trickier because our original derivative did not have constant length. So unit normal vector was something whose length involved the variable t. Now, from our work from earlier, we had the unit tangent vector as this one. Magnitude, we had 10t plus 1, comma 2, comma 1. That derivative was not constant length. So in order to make it constant length, we had to multiply by 1 over square root of 100t squared plus 20t plus 6. Now, when we take the derivative, I can multiply by a constant real number, but that's not going to help me in this case because I have variables inside this length. And so essentially what I'm going to have to do is I'm going to have to take a derivative of the tangent vector, and it's going to be tough to do. Now, I want you to notice that this tangent vector is created by doing a function multiplied times r prime of t. So taking a derivative of the unit tangent vector is like taking a derivative of a function, a real valued function, that's my 1 over magnitude, times a vector valued function. That's my r prime of t. So what I'm going to do is I'm going to use the product rule to take my derivative. The product rule with a real valued function and a vector valued function is found by doing f prime times this original function. So we do f prime of t times my r prime plus the normal f of t multiplied times the derivative of this function. The derivative of this function is the second derivative of r. So the second derivative of r of t. Okay, so I'm going to use that feature, use the product rule in order to try to make my work a little bit easier. Sometimes that works out, sometimes that doesn't work out. So let's take a second derivative of my vector valued function. If I take a second derivative of my vector valued function, I end up with 10, 0, 0. That's a nice thing to deal with. This is not too bad either. 10t plus 1, comma 2, comma 1. My function f is this one. Now I'm going to rewrite that. So that's my f of t. Whoops. I'm going to rewrite that so that it's easier to take the derivative of. That I'm going to rewrite as 100t squared plus 20t plus 6, all raised to the negative 1/2 power. That means when I take a derivative of f of t, I get negative 1/2 times 100t squared plus 20t plus 6, all raised to the negative 3/2 power. So that's what I get for my f prime. Now just, I want you to note, oh, I'm sorry, multiplied times derivative of the inside function. I have to do the chain rule. So I have to take 200t plus 20 when I multiply it times the derivative of the inside function because of the chain rule. Forgot to complete the chain rule. So normal function is this one. Derivative of that function is this one. And I'm going to simplify that derivative just so we can see it a little bit better. Negative 1/2 can be multiplied by 200t plus 20 to give negative 100t minus 20. And then I'd multiply times 100t squared plus 20t plus 6 to the negative 3/2 power. And so that's how I'm going to use it. Hopefully that makes sense. Again, I have to use chain rule. Take the coefficient out front, lower the exponent by 1, and then multiply times the derivative of the inside function. All right, so that means, this is going to be a long one. That means if I want to find t prime of t, the derivative of my unit tangent, I have to take f prime, this whole mess, and I need to multiply it by r prime, which is 10t plus 1 comma 2 comma 1. Let's go ahead and do that. And then I need to add my normal f multiplied times my vector r double prime, which is 10, 0, 0. And yes, this looks messy, but now that I've taken my derivative, I can shorthand some things and use a little bit of common knowledge to simplify what I'm going to do. I'll show you what I mean by that. So here I have my derivative of the tangent vector, the derivative of the unit tangent vector, and it's a big, long, messy expression. Now, I know my normal vector is going to be determined by the derivative of that tangent vector times some scalar. And I know my unit normal vector is going to have length 1. Therefore, I don't really need the derivative of the tangent vector. I just need some vector that's in the same direction as the tangent vector. And if I can make that thing in the same direction as the tangent vector, as the derivative of the tangent vector, excuse me, then what I could do, if I had some vector, let's call it u, if u is in the same direction, let's make that an overline vector looking thing. So if u is in the same direction, then I could simply do that. I could take some vector u that is in the same direction as the derivative of my unit tangent vector. So that's what I'm going to do. I'm going to find the direction of the derivative of the unit tangent vector, and I'm going to use that. Now, what that lets me do is focus on factoring out a common value and getting a coefficient there. So here's how I'm going to do it. notice that I have this 100t squared plus 20t plus 6 raised to the negative 3/2 power as part of the coefficient on this piece. And I have 100t squared plus 20t plus 6 to the negative 1/2 power as the coefficient on this piece. So if I multiply by 100t squared plus 20t plus 6 to the negative 1st power, and then also multiply 100t squared plus 20t plus 6 to the positive 1st power. Well, this negative 1 and positive 1 exponents will cancel each other out, and I'll get 100t squared plus 20t plus 6 to the 3/2 power when I multiply those two. And then what I can do is, since I have a common factor, that's this ugly thing right here, I can pull that whole thing out. So I can take 100t squared plus 20t plus 6 to the negative 3/2 power. I can factor it out, and what I'm going to be left with is negative 100t minus 20 times this vector, writing that down, plus 100t squared plus 20t plus 6 times this vector. And now I can create some sort of a u vector in the same direction, and I can kind of ignore this. So this is my t prime rewritten. So I know that there's going to be some vector u, which is in the same direction, which is that, because that is just the scalar times this vector here. Now there's other ways to do that as well. I did it maybe a longer way than others would. Another way to approach this is to go back to the beginning here. That was, remember, our capital T prime. And I could have just multiplied this by 100t squared plus 20t plus 6 to the positive 3/2. And if I multiplied this entire vector by 100 t squared plus 20t plus 6 to the positive 3/2 power. Well, that would have eliminated this piece. And if I take times positive 3/2 power, I just get this times positive 3/2 times the same thing to the positive 3/2 power would give me this thing to the first power. So if you want to see it that way may be easier than factoring out a 100t squared plus 20t plus 6. You could multiply in, or you could factor out. Doesn't matter. But the point is, this piece gets canceled, and this piece then has exponent of 1. I'm going to do it that way. I think that's a better way maybe to see it for most people. So I multiply, and when you do that, this goes away, and this exponent, 3/2 plus negative 1/2, that exponent becomes a 1. So my u of t that is in the same direction as t prime is this one. And this one I can calculate with in a fairly straightforward manner. Now also notice that almost everything is a multiple of 10. So I'm going to do one more multiplying in. I'm going to multiply everything by 1/10. Again, just to hopefully make life a little bit easier. If I take 1/10 times this first vector, so I'm going to get a new u. I'm going to get a new vector u. And that is going to be negative 10t minus 2 times my vector 10t plus 1, 2, 1. When I multiply 1/10 times this thing, I'm just going to take and multiply by that 10. I'm going to multiply the vector by 10. I'm using the associative property of multiplication with scalars and vectors to do that. So I'm getting plus 100t squared plus 20t plus 6 multiplied times the vector 1, 0, 0. So now I have this new u. Maybe I should rename this one to some other thing. I don't know. Vector other u, or let's say vector w. So now I have a vector u. And what I'm going to do is I'm going to clean this up just a little bit by multiplying through, using some polynomial algebra. Negative 10t minus 2 times 10t plus 1. When I multiply that in and distribute it, and then I'm going to take 100t squared plus 20t plus 6 and multiply that in and distribute it. So on this first one, negative 10t times 10t becomes negative 100t squared. Negative 10t times 1 gives you a minus 10t. Negative 2 times 10t gives you negative 20t. Negative 2 times 1 gives you a minus 2. That's just the x component. By the way, we can combine these terms and get minus 30t. The y component, you take negative 10t times 2, that's negative 20t. And then negative 2 times 2, that's negative 4. In the z component, you take negative 10t minus 2 and multiply it times 1. That's negative 10t minus 2. For the other part of the vector, the part that's going to be added, I take this polynomial times 1. That's 100t squared plus 20t plus 6. And then I take that polynomial times 0. That's just 0. And take that polynomial times 0. That's just 0. Notice what's going to happen when we combine terms to simplify the u. We're going to get a little bit nicer thing in my x component. Negative 100t squared plus 100t squared cancel each other out. Negative 30t plus 20t gives me a minus 10t. Minus 2 plus 6 gives me a plus 4. In my y component, I get negative 20t minus 4. And in my z component, I get negative 10t minus 2. If I wanted to, I could have multiplied through here, multiplied everything through by a 1/2 and made even a little bit simpler of a u. I don't need to right now, but I could have. All right, so I just realized something. I knew something was wrong here, and it turns out I had made a really simple math mistake way back up at the beginning. Let me go through my math mistake. Something looked off. When I took 200t plus 20 and multiplied it times negative 1/2, I wrote down negative 100t minus 20. But if I'm multiplying by negative 1/2, that should have been a minus 10. Now, the nice thing is, the way I did this, when I did my t prime, I could go back and change my mistake. Again, this t prime, going from t prime to u, I have to take the derivative, and as long as I go in the same direction, I'm good. I think the easier way to calculate is to multiply by a constant number, and that gives me another u in the same direction as t prime. The constant number I chose is 100t squared plus 20t plus 6 to the 3/2 power. Notice this piece kind of was left the same. Because when I multiplied by that, it got rid of this, and it gave me 100t squared plus 20t plus 6 to the 1 power to the first power in front of the 10, 0, 0 vector. But this part was not changed. So I can go back and fix my mistake there. And then when I multiplied by 1/10, this vector by 1/10, I can change my mistake here. And 1/10 times this would have given me a -1. When I distribute that, it turns out negative 10t minus 1 times positive 10t plus 1. That gives me a new x component. That would give me negative 10t times 10t. That gives me negative 100t squared. Negative 10t times 1 gives me minus 10t. Negative 1 times 10t gives me another minus 10t. And then minus 1 times 1 gives me a minus 1. So I screwed that thing up. I should not have gotten a minus 30. I should have gotten a minus 20 in front of my t. But that's the only part up till this point where it throws me off. Now when we combine like terms, it's even nicer. Negative 100t squared plus 100t squared gives me 0. Negative 20t plus positive 20t gives me 0. Negative 1 plus 6 gives me a 5. So if we're talking about a vector in the same direction as t prime, this is going to be that vector. And again, all I'm doing is I'm taking the t prime and then multiplying by a few constants to make my life easier. That won't be the same vector as t prime, but it'll be some constant times that vector. Now let's go and ahead and calculate my normal vector from this. That's a long mess, I know. That's okay. That's going to happen sometimes. So the vector I'm going to use is my u that I found. That's in the same direction as t prime. That's going to be 5, comma, negative 20t minus 4, comma, negative 10t minus 2. And then the length of that vector is going to be the square root of 5 squared plus negative 20t minus 4 squared plus negative 10t minus 2 squared. If I wanted to multiply that out and simplify, I can. That's perfectly fine if you want to expand what's underneath the square root, but I'll leave it as that for right now. Obviously, this unit normal vector is a messy vector, but the important part is the direction. And if I just look at 5, negative 20t minus 4, negative 10t minus 2, that gives me a direction that I can use. And then we scale it and make it length 1. Some people actually say, well, let's not calculate the unit normal vector. Let's just calculate a normal vector. And if you lop off this coefficient, this is a normal vector. it is going to be orthogonal to the tangent vector, but it's just not going to have length 1. So sometimes people will find a normal vector and not worry about making it unit length. Now I've graphed this on the graph of the function earlier. Again, I've not made these unit length. If they're unit length, they wouldn't look quite as long. What I've done is I've just created a tangent vector, and then I've created a normal vector. Notice how the tangent vector is going to be orthogonal to the normal vector. And I also want you to notice that in this case, the normal vector and the tangent vector are creating essentially the plane that the graph is in. They're in the same plane. In the other example that we had, what had happened is because our curve doesn't exist in a single plane, the tangent and the normal vector are going to give you orthogonal vectors. And if you look at where the tangent and the normal vector create, they're actually creating, if you look at the plane they create, they'd be creating a plane in which the acceleration vector exists. We'll go over that a little bit later, but that's what it is. Just wanted you to see, because there's lots of vectors orthogonal to the tangent vector. Lots of vectors orthogonal to the tangent vector in three-dimensional space, but the normal vector is the one that's pointing towards the concave side and is in a specific orientation. So you can see how these go around. They're going to always be orthogonal. And they're always going to be such that the tangent vector is moving in the direction of the curve. The normal vector is moving in an orthogonal direction, but it's this specific orthogonal direction where we have the concave part of our curve pointing in towards the concave part, and in this plane. And they're creating this plane. Now, hopefully we see that this is really messy. This normal vector is really messy. And oftentimes they do come out that way. Oftentimes they're going to be messy. It's not a nice thing. In our previous example, our first derivative had a constant length. The previous example is the one that involves sines and cosines. So our derivative had constant length. In this case, obviously our derivative does not have constant length. And so we get a much messier normal vector. We can save ourselves some calculations by multiplying by constants. But make sure you take the derivative first before you start multiplying by the constants, if the constants I'm multiplying by involve variables. If the constants that I'm multiplying by are just real numbers, then I can multiply by the real numbers first. But if my constants involve variables, I need to be careful about that. All right, last thing, we said we were going to find what's going to happen at 1. Well, at 1, let's do this vector calculation first. We're going to get 5, -24, -12. And then if I want to make that, instead of plugging the 1 into this formula, I'm just going to take the square root of 5 squared minus or plus -24 squared plus 12 squared. So I get square root of 745 as the length of this vector. And so 1 over square root of 745 would make a unit vector when I multiply it. If I want to plug in 3, go ahead, let's plug in 3. We get a specific vector, 5. When I plug in 3, I get -64. And when I plug in 3 here, I get -32. And then if I want to make that into a unit vector, I once again just take the magnitude. Again, I like using the magnitude from here instead of trying to deal with this formula. But 5 squared plus -64 squared plus 32 squared gives me 5,145. So there we go. So that's my normal vector, my unit normal vector at 1, at 3, and then in general. Remember, the way to simplify it is after I've taken my derivative, after I take my derivative, multiply by some constants that simplify this vector. I had to multiply by the constant 100t squared plus 20t plus 6 to the 3 halves. That's a constant. I'm not saying it's a real number. I'm saying it is going to be, it's not a vector. I'm multiplying by that expression. So multiply by that expression. That simplifies things. Multiply maybe by a 1/10. That might simplify things by even more. And then we get a vector in the direction of the derivative of our tangent. And I can find the unit normal vector using that vector. Again, a lot of work here in this example. Now, sometimes in R3, there's no getting out of doing a lot of that work, okay? We can do some clever tricks. We can see some nice things. But in R3, oftentimes it's hard to get out of doing long processes to find the unit normal vector. However, in R2, there's a really nice trick. If we have a unit tangent vector in R2, there's only 2 vectors So two vectors, excuse me, that are both orthogonal to the unit tangent and have unit length. So if I know a unit tangent vector, I can simply find a vector orthogonal to that unit tangent, which has unit length, and that must be my normal vector. In R3, there are infinitely many vectors that are orthogonal to a given unit tangent vector. But in R2, there's only two choices. We're either going to swap the x and y components and negate the x, or I swap the x and y components and then negate the y. So which one of these is going to be my normal vector? Well, it's going to be the one that points towards the concave side, the one that's sort of bending in. It's going to be the normal vector is the one that's going to be pointing in towards the concavity. By the way, these have to be unit vectors because this was a unit vector. So if I take t squared plus t1 squared plus t2 squared, I get 1. The negatives aren't going to change that. Therefore, t2 squared, t1 squared add up to give you 1 as well. So in R2, it's a much quicker process to find a normal vector once we have the tangent. So let's compute the unit tangent vector and the unit normal vector for the following function. We have the vector valued function r of t, which is t to the third minus 6, comma, t. All right, so the first thing I have to do is to find the unit tangent vector. So that requires me taking a tangent vector. The one we take is the derivative. So the derivative of this function is 3t squared, comma, 1. So that gives me my derivative vector. That means my unit tangent vector is going to be 3t squared, comma, 1, multiplied times 1 over the magnitude of that vector. Now, if you take the magnitude of that vector, you go 3t squared, quantity squared, plus 1, all underneath the square root. Notice that this is going to be 9t to the fourth. So I'll write it that way. 9t to the fourth plus 1 times this vector. Now, if we tried to do normal vector using the same techniques we did in the previous example, we would have a lot of computations to deal with. But since this tangent vector is a unit tangent vector in R2, all I have to do to find the unit normal vector is to say, well, let's switch the roles of y and x, and then let's negate one of them. So I'm either going to get -1, comma, 3t squared. And by the way, both of these would have length square root of 9t to the fourth plus 1. So if I wanted a unit normal vector, I do 1 over square root 9t to the fourth plus 1 on both of them. Okay. And so I just have to decide which one it is. And the one is going to be pointing towards concavity. So I'm going to do this via via using a graph. You can do this other ways as well. But I'll graph my position function, and then I'll graph my unit tangent vector. Actually, I'll just graph a tangent vector. I'll just graph 3t squared, comma 1. And then I'll see which one of these, either 1, comma, negative 3t squared, or negative 1, comma, 3t squared, points towards the concavity. So this is what I'm getting. I'm getting a point on this graph. This graph kind of looks like something to the third, x equals y to the third. And as you move this point along, this tangent vector you can see in purple. Let me move it to a specific value. Let's say we have our tangent vector at the point 2, or my point on the graph at 2, 2. So we get the tangent vector. If you notice, this is bending slightly in, so I need my unit normal vector to point down and to the right. So we're going to go right and down. That means I need it to have a positive x and a negative y. So I need it to be pointing in this direction. Now this is obviously not unit length, but neither was my tangent that I drew either. So I'm pointing right and down, or down and right. Positive x direction, negative y direction. The one where if I plug in a positive t, I get a positive x direction and a negative y direction is going to be this one. So I know it's going to be that first one because it needs to point towards concavity. It needs to point right and down. So that's that vector. And then obviously this is just a scalar of that vector. So notice that that's much, much easier. And a lot of times people don't even worry too much about the direction, but that is the direction in this case. So sometimes people won't even worry about the direction. They'll say either one is fine because it's orthogonal. But there we go. That's the case. Obviously in R2, this was much easier because I didn't have to take a bunch of fancy derivatives and then scale it and then do other things. So in R2, we can use this trick knowing that the only two orthogonal vectors of length 1 are going to come from switching the x and the y values and then negating either the x or negating the y. So it's a much easier calculation for the unit normal vector in R2 than it was in R3. In R3, sometimes, like in this case, we're going to get some messy looking unit normal vectors. Sometimes in R3, things are going to work out really nice, and our normal vectors are not going to be real hard to compute, like in example 3. But because of this fact, because the normal vector is going to be pointing in a direction that is orthogonal to the direction of the curve, therefore orthogonal to the tangent vector, in R2, it just leaves me one of those two options. Swap the x and y and negate the x, or swap the x and y and negate the y. Now, the last big concept we're going to cover in this section is the application to acceleration. I mentioned this in passing, but it turns out that the acceleration vector for a position function is going to lie in the plane created by the unit tangent and the unit normal vectors. So I can break the acceleration vector into two orthogonal components, one which has coefficient of the unit tangent vector, and the other which has coefficient times the unit normal vector. So I can break down acceleration into two orthogonal components. And this is useful because it tells me how much acceleration is going in the direction of the graph and how much our acceleration vector is pointing in the orthogonal direction to the graph. Now, these coefficients, a sub t and a sub n, can be found by doing what we've done earlier. If I project my acceleration vector onto my unit tangent vector, the formula would be acceleration dot product unit tangent divided by unit tangent dot product unit tangent times the unit tangent vector. Well, unit tangent has length 1, so when I take the dot product of unit tangent with itself, I just get a 1. And therefore, when I project the acceleration vector onto the unit tangent vector, I get acceleration dot product unit tangent as my coefficient of the unit tangent vector. So that means the coefficient of the unit tangent vector, the a sub t that we had on our last slide, is actually going to be just the dot product of acceleration with my unit tangent vector. And my a sub n is simply going to be the dot product of my acceleration with the unit normal vector. Now, that seems pretty straightforward, but remember, sometimes unit normal vectors are hard to find. And so if that unit normal vector gets really messy, we might want to have a different way of calculating this a sub n. And we also might want to have a different way of calculating a sub t if the unit tangent vector is hard to find. And so that's what we do. This a sub t we knew could be found by taking a dot product with the acceleration and unit tangent vectors. But if you work through that, it turns out it's the same as taking the derivative with respect to t of the speed function. Again, r of t is a position function. So the magnitude of the velocity vector is speed, So if I take the derivative with respect to t of speed, it turns out I can find the a sub t that way as well. I'm not going to prove this in general, but you could, if you wanted to, show this if you work through what acceleration does and what unit tangent does and what this magnitude does. Similarly, with a sub n, we know it's the dot product of acceleration with my unit normal vector. There's a number of different ways to calculate a sub n, though. I could take the magnitude of acceleration squared and then subtract a sub t squared. A sub t is this one. And then take a square root of that. I also could take the magnitude of the cross product of acceleration and velocity divided by the magnitude of velocity. And I also could take the magnitude of velocity and multiply it times the derivative of the unit tangent function. So there's a number of different ways to calculate, and sometimes the dot product's going to be the easiest. Sometimes one of these other formulas may be a lot easier. So let's take a look at this example. We'll find the velocity function, the acceleration function for this position function, and then we'll calculate a sub t and a sub n. Now, on this one, we've already calculated our unit normal vector and our unit tangent vector. So it turns out on this one, what's going to be the easiest is probably doing dot products. When I calculate the a sub t, a sub n, on that one, may be easiest to do dot products. So let's check it out. In our previous work, we found the derivative of r of t. We found the unit tangent vector, and we found the unit normal vector. So we need to find the velocity function, which, by the way, velocity is the first derivative. So we can simply say we've already found the velocity vector. The acceleration vector is, well, the second derivative. So we take r double prime of t, and that is my acceleration vector. Whoops. When we do a second derivative, we're going to get -4 times cosine of t -4 times sine of t and 0 as my 3 component parts. Now, this is acceleration. Here we have the unit tangent, and here we have the unit normal vector. So if I want to find a sub t, my coefficient of the unit tangent vector in the acceleration breakdown, it's going to be acceleration dot producted with this vector, which is my unit normal vector. So acceleration dot product with unit normal. So A sub t is equal to, well, this coefficient can be kind of moved out front. So 1 over square root of 16.25. When I do a dot product, remember how dot products work. I'm going to take -4 cosine times -4 sine. That's going to give me 16 cosine times sine plus -4 sine times +4 cosine. That's going to give me a -16 cosine times sine plus 0 times 1/2 becomes 0. And notice that this whole thing just goes to 0. So that means the coefficient A sub t is going to be 0. What about A sub n? Well, A sub n is going to be the dot product of acceleration and my unit normal vector. I'm sorry, this should be a capital N. Notice that my unit normal vector was negative cosine t, negative sine t. This means that A sub n is going to be, well, the dot product gives me 4 cosine squared plus 4 sine squared plus 0. Cosine squared plus sine squared is 1. So if I factor out a 4, I get 4 times 1. And that means my A sub n is equal to 4. So what's this tell me? Well, this tells me that my acceleration vector is going to be pointed in exactly the same direction as my unit normal vector. In fact, it's going to be 4 times my unit normal vector, and there's going to be no acceleration component in the direction of my unit tangent vector. So there's going to be no acceleration in the unit tangent vector direction. All of the acceleration is in the unit normal vector direction. And so all of my acceleration is going to be pointed orthogonal to the direction of the travel, or the direction of the curve. Let's do another example with acceleration. Let's break the acceleration into its component forms. And create a sub t and a sub n with this function. Again, this is r of t. It's a function in R2. We have t to the third minus 6 comma t. We've dealt with this function earlier, and we've found the unit tangent and the unit normal vectors. So again, because we have nice unit tangent and unit normal vectors, I will probably use the dot product calculation for each of these, but maybe I'll show you another way to compute as well, and just to show you that it gives you the same thing. So here we go. So we have our first derivative, which again, if r of t is a position function, then my first derivative is going to give me the velocity function, the velocity vector valued function. Let's do acceleration. That's going to come from doing the second derivative. Which in this case is going to be 6t comma 0. Now, like I said, we're going to use a couple of different techniques to find a sub t and a sub n. The first technique I'll use is the dot product. So let's find a sub t using acceleration dot product with the t. That's a little bit of poor notation, but you get what I'm trying to say, I hope. So I take the acceleration vector, which is 6t comma 0, and I dot product that with my unit tangent vector, which is 3t squared comma 1 times that coefficient. I'm going to throw the coefficient all the way out front, 1 over this square root of 9t to the fourth plus 1. And so we get 1 over the square root of 9t to the fourth plus 1 times, well, when I take 6t times 3t squared, I'm going to get 18t to the third. And when I take 0 times 1, I just get a 0. So that means my a of t coefficient, again, this is going to vary by what value of t I plug in, but it's going to be 18t to the third divided by the square root of 9t to the fourth plus 1. So that's the dot product calculation of a sub t. The dot product calculation of a sub n is going to take my acceleration vector. We already saw that. And multiply it via dot product by my normal vector. This is a sub n, so we're going to use normal vector. Imagine those are vectors instead of just letters there. So we get 6t comma 0 and dot product that with unit normal vector here. That's going to be 3t squared, no, 1 comma negative 3t squared. And then we're going to multiply by the coefficient. I'm going to, once again, throw that coefficient out front. And we end up with 1 over the square root of 9t to the 4th plus 1 multiplied by, well, 6t times 1 is going to give me 6t. 0 times negative 3t squared is going to give me 0. So that means my a sub n, the coefficient of my unit normal vector, will be 6t divided by the square root of 9t to the 4th plus 1. So there I have the coefficients by using dot products. Now, this normal vector was in R2, so it was not really hard to compute. This tangent vector, usually the unit tangent vectors aren't super hard to compute, but the unit normal vectors can be tough. So oftentimes, if somebody asks you to find the a sub t or the a sub n, one of those other formulas may be a little bit easier. Let me show you that they give you the same thing in this case. So let's deal with a sub t using the other formula, and let's deal with a sub n using the other formula. All right, so what other formulas do we have? Well, we have the dot product. We use that one to find the a sub t. So let's find the a sub t using the other formula, derivative of speed, or in other words, the derivative of the magnitude of the velocity function. So my velocity function is 3t squared comma 1. If I want to find the derivative of the magnitude, well, the magnitude is going to be, well, let me make sure I put in the correct amount of steps. So we're going to take 3t squared comma 1, find the magnitude, and then take the derivative. So the derivative, again, with respect to t, of the square root, well, when I take 3t squared comma 1, I take 3t squared squared plus 1 squared. That's 9t to the 4th plus 1. So I'm taking the derivative of that. And that means my a sub t is equal to, well, what we're going to do is we're going to think of this square root as 1/2 power. So 9t to the 4th plus 1 to the 1/2 power. So I take the 1/2 power out front. 9t to the 4th plus 1. I'd subtract 1 from the power and then multiply times the derivative of the inside function. The derivative of the inside function would be 36 t to the third plus 0, or just 36t to the third. That's the derivative of 9t to the fourth. So 4 times 9, lower the exponent by 1. 36 times t to the third, I can multiply that by 1/2. That'll give me 18t to the third. Nine t to the fourth plus 1 to the negative 1/2 power is the square root of 9t to the fourth plus 1 in the denominator. Notice I got the same thing either way. The advantage of this one, the advantage of this formula here, is that I never had to actually know the unit tangent vector to do my calculations. So in this case, I could find my a sub t without ever knowing what the unit tangent vector is. We can do a similar thing with a sub n. We've already done dot products. So we can use one of these other formulas. Maybe I don't want to find the derivative of the unit tangent vector. So maybe I don't want to use that formula. So I could use this formula, although we are in R2, so I'd have to expand this to R3 in order to make it cross product work. So I won't do that one. I won't expand R3. I'll just use this one. And I've already calculated a sub t. So what I can do is take the square root of the magnitude of my acceleration vector squared. Remember, magnitude of acceleration vector, magnitude of my acceleration vector squared. My acceleration vector was the 6t comma 0. So let's write that in. Magnitude squared minus a sub t squared. And we had just found a sub t. It's this thing. So let me go through and replace that with the big expression. Squared. And then it's a lot of algebraic simplification. So a sub n is equal to, well, if I take the magnitude squared, I'm just going to take 6t squared plus 0 squared, and then the square root and this squared is going to cancel each other out. So I'm going to end up with 36t squared minus, if you take 18 times 18, I'm squaring the numerator here, I end up with 324 t to the 6th power divided by 9t to the 4th plus 1. I'll go ahead and simplify that. So I want to put both of these with the same denominator of 9t to the 4th plus 1. So I'd multiply top and bottom of this piece by 9t to the 4th plus 1. So I get 36 t squared times 9t to the 4th plus 1 minus 324 t to the 6th power. Well, when I take 36t squared times 9t to the 4th, I get 324 times t to the 6th minus 324 times t to the 6th. That'll cancel that out. And what I end up getting, let me do one more line. On top, sorry, is 36t squared. So I get 324t to the 6th plus 36t squared minus 324t to the 6th. And in the bottom, I get 9t to the 4th plus 1, which I can take the square root of the top, square root of the bottom. That's going to give me 6t divided by the square root of 9t to the 4th plus 1. So again, I get the same thing. Obviously, this way was a lot longer in this case. Doing this square root formula took a little more algebraic manipulation. Doing the dot product was quicker in this case because I already had the n. But if we don't have the n, this method allows me to get the same answer without ever having to calculate either the unit tangent vector or the unit normal vector. So it's fairly nice when I don't want to calculate those two things. Now let's do the last example of a position function that we've already calculated with. This was the one that gave us a lot of difficulty to get the unit normal vector. Unit tangent wasn't crazy bad, but the unit normal vector was. And so with this one, we'll calculate the a sub t, we'll calculate the a sub n, and we'll try to use the quickest methods possible. The quickest methods possible may be the dot product. They may be one of these other formulas. Now, I kind of know what's going to come up and how the quickest method possible and what the quickest method possible is going to be, but we'll see how this goes. Now, in this case, we already have the tangent, unit tangent, and unit normal vectors. So probably the dot product is going to be the easiest. So the dot product, what I mean by that is a sub t is going to be the dot product of acceleration and the unit tangent vector, which in this case, the unit tangent vector, we have a messy coefficient, and then we have 10t plus 1, comma 2, comma 1. But the acceleration vector is really nice because the second derivative is just 10, 0, 0. So 10, 0, 0. So when I take the dot product of those two things, I am going to get 1 over, so I'm going to get the ugly coefficient, but dot product 10 times 10t plus 1 gives me 100t plus 10, but 0 times 2 gives me 0. 0 times 1 gives me another 0. So I end up with 100t plus 10 divided by this ugly square root when I do the dot product. So that was pretty quick. In a similar way, we could do the a sub n by taking the dot product of acceleration with my normal vector. That can be done. Again, it's pretty easy to do, to be honest with you. But because we haven't done one of the other types yet, I'm going to do one of the other types. So let's get the formulas for a sub n. So here are the formulas to calculate a sub n. Make that easy. I said we could do the dot product. I'm not going to do the dot product just because we've already done a lot of those dot products. We just did one where we used the square root, so I'm not going to do that one. This one involves the derivative of the unit tangent. That doesn't seem like it's going to be fun to do. So that leaves me with this. My a sub n can be found by using the cross product of the acceleration and velocity vectors divided by the magnitude of the velocity vector. You can also say that's the speed. So I'm going to kind of do some work off to the side. I want to do the acceleration, cross product, the velocity vector. Remember how to do cross products. Again, I'm going to sort of simplify my notation. We got to put I, J, K in the first row. In the second row, I need my acceleration vector. Well, that's a really nice vector, 10, 0, 0. And then in the third row, I'm going to put my velocity vector, which is 10t plus 1, 2, 1. So what that's going to give me, well, when I find the coefficient of I, which is the x component, I'm going to be going 0 times 1 plus 2 times 0. That's just a 0. The coefficient of j is what I get when I take the negative of 10 times 1 minus 10t plus 1 times 0. So that's just a negative 10. And then the coefficient of k, I'm going to take 10 times 2, which is 20, plus 10t plus 1 times 0. So that's just 20. So that cross product is a pretty good vector to deal with. It is 0, negative 10, 20. How about the velocity vector? Well, I already knew that the velocity vector is this. So if I see the cross product and I see the velocity vector and I want to calculate a sub n is just the magnitude of that cross product divided by the magnitude of the velocity vector. So magnitude of the cross product is going to be the square root of 0 squared plus negative 10 squared plus 20 squared. Magnitude of my velocity vector is going to be the square root of 10t plus 1 quantity squared plus 2 squared plus 1 squared. If you remember, we've actually already done the calculation. We've simplified the calculation in our denominator. When I multiply this, I get 100t squared plus 20t plus 1. And then the plus 4 and the plus 1 are tacked on. So that altogether becomes a plus 6. And the numerator is square root of 500. Again, in this one, the cross product of acceleration and velocity is pretty nice. So we can deal with this. By the way, you might think, well, dot product has always worked and dot product will always work, but sometimes these things get fairly ugly. Sometimes these things are hard to calculate. Moreover, let's imagine I wanted to calculate an a sub t and an a sub n for a specific t value, a specific value for my variable. It may be easier to do a cross product with numerical values in here and then do the magnitude of that than trying to do derivatives of unit tangent functions. So if we're looking for specific values of t, then it might, if we're looking at specific values of t, it might be more useful to use one of those other formulas. So this is pretty easy calculation. This is a pretty easy calculation. This is a pretty easy calculation if these vectors are ones where we've already plugged in a specific t value. Now this one can't be done by plugging in a t value and then taking a derivative. This one is going to be just as difficult. But these two in particular, these middle two here, are pretty efficient when we're just plugging in values of t. Now, the last thing I want to do, or at least I want to talk about, is this. This is an equation that tells me that my acceleration can be broken down into orthogonal pieces. One piece in the direction of the unit tangent and one piece in the direction of the unit normal. But it's also an equation where we have essentially 5 unknowns. The acceleration vector is an unknown. The unit tangent vector is an unknown. The unit normal vector is an unknown. A sub t is unknown. A sub n is unknown. We, on one of our examples, had a very difficult time getting the unit normal vector. There is a possible scenario where you can find the unit normal vector by utilizing this equation. You could find the acceleration, you could find the a sub t, you could find the unit tangent, and you could find the a sub n, and then you could solve for the unit normal vector. Now, I'm not going to do that on this video, but if push came to shove, we could do that. Sometimes that might be more efficient than going through taking a derivative of the unit tangent vector and then trying to make that unit size or have size 1. So that's unit tangent and unit normal vectors. We see their applications in acceleration. We know that they have to be orthogonal. So in R2, that gives us a really nice way of finding the unit normal vector if we know the unit tangent vector. In R3, we're going to have to find the unit normal vector by taking a derivative of the unit tangent vector and then multiplying by the length of that. Again, this would also work if we multiplied times any constant number after we took the derivative. And then the unit tangent vector is a vector that is tangent to our vector valued function of length 1. So it's the derivative vector made into a vector of length 1. So that is the end of this video. Hopefully, we learned something about unit tangent and unit normal vectors.